Today, I will be presenting a formalization of opaque definitions for a dependent type theory. This is work done at Chalmers University of Technology and the University of Gothenburg in Sweden. So to begin with, what is a definition? In Agda, a definition consists more or less of three parts: a unique name, which is used to refer to the definition; a definiant, which is the term that gets bound to that name; as well as a type annotation for that given term. This works both at the term level, as with this doubling function here, as well as at the type level, which we might call a type alias. Here, we define a positive natural to be a natural number n, paired with a proof that n is greater than 0. A key property of these definitions is that they can be composed, in the sense that a later definition can reference an earlier one. So here's a classic example. Starting from the usual unary natural numbers, we can build a number hierarchy, with each layer defined in terms of the previous one. So we can define integers as differences of naturals, where x comma y represents the integer x minus y. Then define arithmetic inequality in terms of these operations on the natural number type. Then we can define the rationals as the field of fractions over the integers, with the usual equality relation given in terms of the operations on the integers this time. So now let's say that we want to show that this equality relation on the irrationals is symmetric. This would be a proof obligation. Given a proof that x equals y, how do we produce proof that y equals x? A reasonable first step might be to ask Agda to normalize the goal type for us, which gives us this. And that's not very readable, right? So what exactly is going on here then? Well, when Agda normalizes a definition like equals q, it unfolds it, replacing it with its definitions like this. But now we have an equals z that also needs to be unfolded, so we get this. And then finally, unfolding times z, we get that big block of text from earlier. Essentially, the problem is that we've gone from this high-level concept of equality on Q all the way down to the lowest level of operations on the naturals. And to be precise, the problem is twofold. First, while it's fairly cheap to unfold any individual definition in an expression, the process of repeatedly unfolding all of the definitions in many deeply nested expressions can quickly blow up, costing considerable time and memory in the type checking process. And on the other hand, I, as the programmer, am also not very fond of this block of text. As a goal type, it's not very readable, nor is it terribly enlightening as to exactly what it is that I'm trying to prove. So what recourse do we have? One possibility is to adopt opaque definitions, which are simply definitions that do not unfold. In Agda, this is accomplished using the opaque keyword like this. But of course, if the definition never unfolds, then we can't meaningfully reason about it. So we can use the unfolding keyword in the context of another opaque definition to declare that inside of this scope, we do want the definition to unfold. So the idea then is to define a sort of interface to the opaque definition that allows outside code to reason about it without having to explicitly unfold it. For example, equals z and times z here can be thought of as part of the interface to z. Then when we're consuming z elsewhere, we can just use this interface like so. And the key thing here is that we haven't actually given an unfolding clause for z anywhere, and so it will not unfold during type checking. And to see what this means for us, we can look at our symmetry theorem again. Since we want to reason about the internals of equals q, we make sim q opaque and then add the corresponding unfolding clause. And then if we ask Agda to normalize the goal type again, we get this time. So note how it's given in terms of the operations on z now rather than on n. And in fact, if we take a look at the unfolding chain from before, we can see that this goal type is what we got after only the first unfolding step for equals q. Since we didn't ask the type checker to unfold anything else, this is as far as it will go. So the upshot of all of this is that the opaque definitions seem practically useful. We can use them to locally control unfolding, which can help improve both type checker performance as well as the user experience. But the question then is of whether they're actually semantically sound or not. In particular, since it changes the way that definitions reduce, it's conceivable that opacity could have an impact on subject reduction, and this is the question that we're going to seek to answer here. So our contribution is as follows. We give a formalism for top-level opaque definitions, which is based on the way that opaque definitions are implemented in Agda. And moreover, we have a full formalization in Agda of a dependent type theory with support for these top-level opaque definitions using our formalism. It builds on the existing graded type theory project, a formalization of a graded model-dependent type theory, which in particular lacks support for definitions of any kind prior to our work. And finally, using this formalization, we've established a number of desirable properties of the type theory, including the aforementioned subgrid reduction, as well as normalization, consistency, decidable type checking on a certain fragment, and so on. So let's start by talking about how we formalize definitions without opacity. Here's a quick overview of our core language. For the most part, it's a fairly standard dependent lambda calculus. The interesting part is the addition of definition names alpha, which are treated in much the same way as variables x. There's a minor difference in that variables are represented by de Bruijn indices, whereas definition names are represented by de Bruijn levels, reflecting the fact that definitions are invariant on their binders. So what is it that these levels are actually indexing? We define a definition context nabla to be a list of definitions in much the same way that the usual typing context gamma is a list of variables. And each entry in nabla is a pair of a definitions t and a type annotation a. We can see that this is in fact exactly the same information that's contained in an Agda definition, shown here with t equals lambda n plus n, and a equals nat to nat. These definition contexts will carry information about all of the top-level definitions that are available in the environment. And since the typing rules for definition names will need to look into the definition context, we'll introduce the nabla now into each of our typing judgments, like so. And we'll also need a new well-formedness judgment for a definition context, which is defined as follows. A definition context is well-formed either when it is the empty context, or when it's a well-formed context nabla extended with a new definition t annotated with a, such that t is a well-typed term of a. And since we're considering top-level definitions, this happens in the empty typing context, since there are no variables to speak of. Additionally, we modify the well-formedness rules for typing contexts, so that the empty case requires a definition context to be well-formed. This dependence of typing context on definition context makes sense when you consider that a variable may have a type given by a type alias, such as int equals nat times nat. As an example, consider the definition context with the two definitions double and quadruple as shown here. To show that it's well-formed, it suffices to show that in the empty definition context, the term lambda n plus n, which is the definitions of double, is a well-typed term of nat to nat. And then that in the definition context containing double now, the term lambda n double n, which is the definitions of quadruple, is also a well-typed term of nat to nat. So now let's take a look at our new typing rules. The defin rule here states that in a well-formed context, a definition named alpha is a well-typed term of a exactly when it refers to a definition annotated with a in nabla, which is what this notation here means. Essentially, this rule is stating that a definition gets its type from its type annotation. So for example, in a context with double, alpha naught refers to double, which is annotated with nat to nat. And so we can conclude by defin that alpha naught is a well-typed term of nat to nat. Next, the delta reduction rule states that in a well-formed context, if a definition named alpha refers to a definition with definitions t and type annotation a in nabla, then alpha is actually equal to t as a term of a. And this rule is, of course, what gives definitions their substance. So using the same example here, we know that alpha naught refers to double, which has the definitions lambda n plus n. And so we can conclude by delta reduction that alpha naught is actually equal to lambda n plus n. And finally, we have another variant of delta reduction, which applies to the actual reduction relation. So it's essentially just a directed version of the previous rule, which states that a definition name reduces in a single weak head reduction step to its definitions. And that's about it for top-level definitions, really. We have two rules governing the well-formedness of definition context, and then three rules giving meaning to definition names. So now, how do we get opacity into the mix? To begin with, we'll need to mark each definition as either opaque or transparent. And to do this, we augment the extension case for definition context to include an opacity omega, which is either opa, meaning opaque, or tra, meaning transparent. We'll also need to keep track of which other definitions an opaque definition wishes to unfold. And so the opaque case includes an unfolding vector phi, which is a bit vector demarcating the prior entries in the definition context, which have been named in unfolding clauses. This should be a bit easier to make sense of with an example. So let's suppose that we have a definition context with the three definitions z equals z and sim z as shown here. Since all three are opaque, all of the context extensions will be marked with OPA, like so. And for Z, there are no prior definitions to unfold, so the unfolding vector is simply empty. For E equals Z, there is an unfolding clause for Z. So the unfolding vector will have a 1 in the first position, indicating that it wants to unfold Z. And then for sim Z, there's an unfolding clause for equals Z, but not for Z itself. So the unfolding vector will have a 0 in the first position, and then a 1 in the second position. To actually use the unfolding vectors in the typing rules, we'll define now the transparentization operator, which expresses how unfolding vectors act on definition contexts. The idea is that an opaque definition lives in a context that has been transparentized by its unfolding vector. And what this means is that prior definitions that it's asked to unfold will now appear transparent to it. Of course, the empty case is trivial. And in the no case, we consider a vector phi with a trailing 0, meaning we don't want to unfold the outermost definition. And in this case, we don't need to do anything, so we just copy the definition from the input to the output without touching its opacity omega. And then continue on with phi on the rest of the definitions. In the yes tra case, we consider phi with a trailing 1, meaning that we do want to unfold the outermost definition, but the definition is already transparent, so there's nothing to do. We just copy it over, leaving it transparent, and then continue. The interesting case then is the yes opa case, where phi has a leading 1 and the next definition is opaque. In this case, we copy it over, turning it transparent in the process, and importantly, we continue not just with phi, but with phi joined with the definition's unfolding vector phi prime. And this joining operator here is just bitwise disjunction. It enforces the property of transitive unfolding. What this means is that when a definition unfolds another definition, it also implicitly unfolds all of the definitions unfolded by that definition, and so on and so forth. And we'll see why this is important later, but first let's take a look at an example. So suppose that we want to apply the unfolding vector 1, 0, 1 to this definition context from earlier. First, since the vector is a trailing 1, we want to apply the yes opa rule to make sim-z transparent. Thus, we join the leading part of the running vector with sim-z's unfolding vector to get 1, 1. And then, since there's still a trailing 1, we can apply yes opa again to make equals z transparent. And again, we join the leading part of the running vector with equals z unfolding vector this time to get 1. And then finally, we apply yes opa one more time to make z itself transparent. And so thus, we can say that 101 transparentizes this context to make everything transparent. And we can see transitive unfolding in action here in that we made equals z transparent, despite the original unfolding vector having a 0 in the second position. Since sim-z wants to unfold equals z, the join in the first step placed a 1 into that second position, and so we ended up unfolding it anyways. Now to account for opacity, we split the extend case of the well-formed misjudgment into a transparent and an opaque case. In the transparent case, it's exactly the same as before, but in the opaque case, we now need to transparentize the context in which the definitions is checked, so that the prior definitions it's asking to unfold will correctly appear transparent. Note that the type annotation is still checked in the original context. This is necessary to prevent the definition's type from leaking any implementation details of the things that it unfolds. So for example, consider this lemma. For the type annotation to make sense from an outside perspective, it would either have to be the case that these pairs here can be typed with a z, or that equals z can be typed as a binary relation on pairs of naturals. But neither of these things can possibly be true without unfolding z, so that type annotation actually is ill-formed. Now for the typing rules, if we redefine the maps to relation here to only hold when the definition in question is transparent, it turns out that the exact same typing rules just end up working. So the defin rule still works anywhere, but the delta reduction rule will only go through when the definition is transparent, giving us the desired mechanism for controlling unfolding. So now let's talk about some results. Our key technique for reasoning about normalization is a Kripke logical relation. Roughly speaking, the idea is to define increasingly stronger variants of the typing judgments that characterize terms by their weak head normal forms. Then by proving the fundamental theorem of logical relations, it's possible to show that all of the variants are in fact logically equivalent. And this is actually one of our core results, that our extensions to the type theory preserve the fundamental theorem. So a few normalization related consequences fall out of this. Of course, we have the usual normalization theorem, which states that any well-formed type or any well-typed term reduces to some weak head normal form. And we also have canonicity for the natural number type, which states that in fully transparent contexts, all natural number terms are equal to numerals. In particular, this requires transparency because it might be the case that an opaquely defined natural number does not reduce because of its opacity. And finally, we have consistency in the empty context, a form of canonicity for the empty type. Now you remember that bit about transitive unfolding from earlier? The main reason to enforce transitive unfolding is this theorem here, which states that well-formedness of definition contexts, as well as certain other typing judgments, are preserved under transparentization. And this is analogous, in some sense, to subject reduction for transparentization. And in fact, we also show that with explicit unfolding, that is, the system where we only unfold exactly what we ask for and nothing more, there exists a transparentization from a well-formed definition context that gives back an ill-formed one. Some other miscellaneous results include the usual sense of subject reduction, which states that types are preserved under weak head reduction, as well as decidable conversion, which states that given two well-formed types, it's decidable whether or not those types are judgmentally equal. And moreover, given two well-typed terms of the same type, it's decidable whether or not those two terms are judgmentally equal. And finally, decidable type checking, which simply states that on a certain checkable fragment of the language, all of the basic typing judgments can be decided. In particular, the formalization contains a bidirectional type checker, which we have now extended to account for definition context. So in summary, we've given a formal characterization of top-level definitions, which may optionally be marked opaque to restrict unfolding. We've implemented the formalism as an extension to the graded type theory project, which in fact has now been merged into the main project with certain changes. And we've shown that our extensions preserve many of the desirable metatheoretic properties of the theory, including subject reduction, normalization, consistency, and so on. And finally, we have a full mechanization of the formalization in Agda. If you want to check out the code, you can take a look at the Zenodo record linked below, or the version of the code bundled with the paper. Alternatively, you can check out the GitHub repository if you want to see the development version of the code. Thank you for your time, and have a fantastic evening.
Let's turn to the speaker.
Let's just confirm the speaker. Okay. Also, could you turn on microphone so that you can answer questions?
Yes, yeah, you can hear me?
Yes, thank you.
Good.
Any question?
Please come here and up.
So that is microphone.
Yeah.
So
Can you hear me?
Yes, I can.
So in the system as presented here, this concept of opacity only applies to top level definitions, right? Is that
Yeah.
Is there a fundamental like reason why it only works at the top level, or could you have like local definitions inside of something else also be opaque or something? I don't know why you'd want that, but just wondering if it's like possible.
Yeah, it is possible. In fact, there are some systems out there that implement it, like the rock type theory. But we elected to go with only top level definitions for this project. One, because it better models how Agda works. It only supports opacity for top level definitions. And two, because the formalism is slightly simpler. One thing to note about having local definitions is it's possible to have interdependencies between variables and top level definitions, because you could say have a variable be a type variable, and then you would have a local definition that depends on the type variable, since the definition is typed with that type variable, right? Which means you would kind of have to intersperse the definitions and the variables in some kind of heterogeneous context somehow, which is a little bit complicated. But in principle, there's nothing actually stopping you from it if you want to go through all of that trouble, yes.
I see. Okay. Thanks.
Yeah, so on that point about it modeling Agda closely, what about parameterized modules? Because then you are extending the context, right? You can introduce additional variables, and in that circumstance, you know they're not going to depend on the definitions at the same time, right?
Right. We're sort of in some sense thinking about an idealized version of Agda where it's mostly just the basic calculus and not any of the fancy types or module system stuff. But
I'm wondering if parameterized modules would be easier to figure out than local definitions.
probably,
Yeah, okay,
I'm not sure. I haven't really thought about it.
okay, thank you.
Sorry about that.
Okay, I read the question. When all definitions are transparent, if I understand correctly, two terms are either equal or observationally distinct. With opaque, now there are cases where we cannot prove equality, but in fact the terms are not distinguishable. This could create issues in implementations that baked in the assumption that non-equal or incompatible implies distinct. Do you know if this has been people in practice?
I don't think I caught that. Is it possible to maybe type the question in the chat box?
Okay. You have access to, I'm sorry, this copy.
Oh no, I'm not in it. Sorry.
Maybe this copy to the Zoom. Yeah, let's copy the question. Oh, okay.
Okay, thank you. When all definitions are transparent, if I understand correctly, two terms are either equal or observationally distinct. With opaque, now there are cases where we cannot prove equality, but in fact the terms are not distinguishable. This could create issues in implementations that baked in the assumption that non-equal implies distinct. Do you know if this has bitten people in practice? I do not know. I don't think I've actually seen that in practice. I don't think I can provide any more information about that. I'm sorry.
Okay, maybe the first. No, okay. So it's 5 minutes or so left. Other questions? So this is our last chance for questions. So maybe I can ask a very general question. So as I understand, you have added the opaque to a specific type system. But if we want to add similar like opaque definitions into other type theories, like how could your approach be generally applicable to them? Or do you foresee any difficulties in adopting your approach in other type systems?
No, we think that it should be fairly generalizable. And in fact, you could even, I think, remove the dependent part of the type theory to create a sort of non-dependent definition system in any sort of type theory you want.
Okay. Yeah, cool. Thank you. There's no other questions. Let's thank the speakers again. And, this concludes this.
Thank you. Have a good evening, everyone.